with few existential threats more concerning than nuclear radiation.
Nuclear radiation is not an existential threat. It's time for some more megaprojects. Specifically, South Korea has a problem. When will the next nuclear meltdown happen? So nuclear engineers look at risk profiles and can tell you the probability of meltdown, which is quite low. For those of you who don't know me, I'm Tyler Folse. I'm a nuclear engineer with a little over 10 years of experience in the commercial nuclear power industry. From engineering to operations to emergency response. I don't mention everything there is nuclear, but I can certainly share some knowledge. Let's see.
Nuclear power plants represent one of humanity's greatest engineering achievements. These facilities
They really do.
harness the heat emitted by the breakdown of radioactive fuel to provide affordable electricity to about 10% of the world's population. However, the cooling systems responsible for regulating this heat are not perfect. These systems can fail and give rise to a chain reaction in which the nuclear fuel melts and destroys its containment, releasing deadly radioactive particles that...
Okay, a nuclear meltdown is not an uncontrolled chain reaction. It's a loss of cooling that leads to overheating. It's not the same thing as a runaway fission reaction leading to prompt criticality, which is what blew the roof off of Chernobyl. That is something entirely different. That is when you add so many forms of reactivity to a nuclear reactor all at once that just the prompt neutrons from fission cause a chain reaction by themselves. And yeah, by prompt, I'm talking 10 to the minus 15th power seconds. So that's going to run itself out of control really quickly. On the flip side, if you're designing a nuclear weapon, you want that. But that in itself isn't the meltdown. The meltdown at Chernobyl wasn't the most severe aspect of that. That would be the prompt criticality was the initial condition that led to a massive steam explosion combined with lack of a real containment structure that created the mess that was the Chernobyl accident.
Spread far and wide.
Another thing is containment isn't automatically destroyed. Chernobyl didn't have a true containment structure that was designed to withstand that kind of energy. Modern nuclear plants have multiple fission product barriers, which includes the reactor fuel cladding itself, the reactor coolant system and reactor pressure vessel, and the containment structure, the dome that prevents it from escaping into the environment. And probabilistic risk assessment data shows containment failure is order of magnitude less likely than fuel damage, which is the proper engineering term for meltdown. But again, meltdown is caused by fuel overheating, not runaway fission reaction. Now, Chernobyl had both, but the much worse aspect was the runaway fission reaction, which is not possible in modern nuclear plant designs. The fuel just simply doesn't have enough energy to rapidly multiply like that.
This event is known as a meltdown, and it is one of the most terrifying man-made...
By popular culture as a meltdown, sure. So I will again, terms such as fuel damage or core damage, because the core consists of the nuclear fuel, are the more proper engineering term. I'm okay with people saying meltdown because that's what the media says, but reactor engineers and risk assessment engineers don't actually use that term.
Disasters that the world has ever seen. Radiation generated by these events can spread rapidly over thousands of miles, leaving extensive damage and death in its wake.
So radiation from these events can be detected from very far away, especially in the case of Chernobyl. That's one of the reasons why that event could not be covered up, is because they're setting off high radiation alarms in Scandinavia. But that doesn't necessarily mean by itself it's going to cause widespread radiation sickness. That's simply because radiation detectors are extremely sensitive. And after all, you want them to be extremely sensitive so you can detect elevated levels of radiation to indicate that, hey, there might be a leak somewhere. You should probably look into that. And to give you a sense, Chernobyl is the only civil accident, power plant related, that caused direct radiation fatalities immediately. In the case of that number, that was 28 immediately from immediate radiation poisoning by itself. Fukushima did not have any radiation-induced deaths. And fallout levels do drop sharply with distance, due to atmospheric dispersion as well as radioactive decay. And some of that depends on the weather, which is why during accident scenarios, you look at wind speed and direction to determine what levels to implement protective action recommendations, such as evacuations or shelter-in-place orders.
Even short-term exposure to radiation can make entire cities uninhabitable and poison farmland for thousands of years.
Short-term exposure and thousands of years in the same sentence. I'm not entirely sure what he means by that, but thousands of years is misleading. Most radioactive isotopes from an accident will have short half-lives on the order of hours. And in fact, that's one of the highest risk events that you look at for nuclear accidents isn't the meltdown, it's the large early release probability. And so that right there is something worse than a meltdown. For instance, during the 3 Mile Island accident, that was a meltdown. The core was damaged, but the amount released was very little compared to something like Chernobyl. And that's because 3 Mile Island did not have a destroyed or bypassed containment. The containment remained intact. There was a lot of fear generated from 3 Mile Island, but as far as actual elevated radiation dose, no. Nothing like the levels you saw during Chernobyl. Now, there are long-lived isotopes such as cesium-137 and strontium-90. Those half-lives are on the order of 30 years, and that's what you're still seeing after Chernobyl, but they do still decay enough for safe habitation. The Chernobyl exclusion zone is still an exclusion zone because it's a radiological controlled area that requires strict permissions and strict monitoring. There are some areas that you do not want to be anywhere near, but as far as the entire 2,600 square kilometers, a very, very small percentage that is actually dangerous. But it is still an exclusion zone because it's a radiological controlled area. That means if you're going to go into it, you need permission and you need to be briefed on where the hazards are located. But by volume, well over 99% of it is perfectly safe, considering how long ago that accident was. That accident happened in 1986.
Furthermore, meltdowns pose a serious threat to human health. Although their immediate impacts are often...
Okay, I'm not going to debate that one. You do not want to be next to a core that is damaged. Of course, you don't want to be next to a core that's operating either, which is why within a reactor building, there is a bioshield within the containment structure. Because you can still go in the containment structure while the reactor is operating, but there's a bioshield, sometimes called the secondary shield wall, that's inside of the building that you do not cross while the reactor is operating. And that's because of the high neutron dose associated with the reactor operating, making fission. Dose is way less when the reactor is offline.
Invisible and might not manifest for decades or even generations. We possess first-hand knowledge of the...
That's possible. Some of it could be latent, but if you're getting that close to fuel damage, to damaged fuel, it's going to happen pretty quickly, minutes to hours, which is why you don't cross, which is why if you're going anywhere near the reactor, you need to have a briefing by radiation protection staff.
Threats posed by nuclear meltdowns, because they have happened before. A meltdown that occurred in 1986 at the Chernobyl nuclear power plant in present-day Ukraine has been linked to thousands of deaths, and victims of this disaster are still being diagnosed with cancer today.
So linked to thousands of deaths in the case of Chernobyl. So direct deaths, there were 28 acute radiation syndrome deaths directly from the accident. Horrific way to go. I don't mean to sound dismissive of that at all. That is one of the most horrible ways to go. And there were also 15 later thyroid cancer confirmed cases. This thousands number, an estimate was conducted in the 2000s that came up with a 4,000 number. That's likely what he's referencing it. And that comes from statistical models using the linear no threshold assumption, which is highly controversial, and it's a pretty big overestimate at low doses. And what that means is every amount of dose of radiation increases your risk of cancer, which is highly conservative when modeling something like Chernobyl. Looking at actual cancer studies, so from the other direction of looking backwards, the number at which an increase of cancer risk is evident is 100 millisievert, which is twice the occupational limit for anyone that works in a nuclear power plant. And that number is per year. So under the linear no threshold model, every banana you eat, which is 0.1 microsieverts, or a year of cuddling your spouse in bed, which is similar on the order of 0.1 to 0.5 microsieverts per year, depending on how hot your spouse is. The linear no threshold says that is very slightly increasing your risk of cancer. So you can see how including normal activities like that is controversial, and I'm going to say highly conservative, to say the least. But if you do use that model, you're going to end up with 4,000 total fatalities from Chernobyl using that, and that also includes people that haven't been born yet. And hence, I'm thinking that's what he's referencing, because he also mentioned new cases being discovered to this day. And something like cancer, it's kind of hard to fingerprint something, especially when you're looking back to an accident that happened in 1986.
Due to the widespread radiation. More recently, extensive damage sustained during a tsunami in 2011 caused a meltdown at the Fukushima Daiichi nuclear power plant in Japan. Radiation from this event could be detected as far away as Germany. And
that is true for detection, but the high radiation alarms that went off in Germany are billions of times lower than harmful exposure. And the trace levels in Europe were millions of times below health concern thresholds. And keep in mind, concern thresholds for a member of the public is 1/50th that of someone that works at a nuclear power plant. So we're talking way, way below the cancer threshold, less than 1%. And really, this is a testament to how much more advanced radiation detectors were in the 2010s compared to the 1980s.
It has already been linked to a handful of cancer diagnoses. Chernobyl and Fukushima.
I can see you linking it, and it can show up, but to say that is a cause, I'm doubtful. You're likely going to get more radiation from working at any other kind of facility, non-nuclear facilities, I might add, if you're going to fingerprint a cancer case in Germany to Fukushima.
Are just two examples taken from 20 partial or total meltdown events that have taken place since the 1950s.
So partial meltdown, so he's including contained fuel damage events like 3 Mile Island Unit 2, which did not have public health impact, and only 3 events, and that includes the Chernobyl, Fukushima, and 3 Mile Island, involved large-scale core damage. And that also tells you how tough the containment structure was at 3 Mile Island, because that was a large chunk of that core. Talking multiple meters of fuel rods were damaged in that accident, and yet the containment building contained it. 3 Mile Island is one that's studied a lot within the nuclear industry because there's so many more enhancements, especially within the United States, that were made both to nuclear plant design as well as reactor operations safety and procedures. Because of accidents like 3 Mile Island, emergency response procedures are symptom-based. So there is a procedure for core damage or for a meltdown. Now, there's a whole bunch of procedures that you look at first that prevent you from getting to that step, as well as safety systems that prevent things from getting that far. But hey, there are contingencies for if that sort of thing were to happen again. And how do you prevent it from escaping into the environment?
And with over 400 nuclear power plants currently in operation throughout the world, it is likely that more meltdowns will occur in the future.
Okay. So I mentioned over 400 nuclear power plants. So let's do some quick probabilistic math. So high risk for a nuclear power plant core damage frequency, and this is something that is modeled using probabilistic risk assessments, and it's taken into account during maintenance schedules, say when you take certain safety systems out of service for maintenance, that you prevent the core damage frequency from hitting 1 times 10 to the minus 6 per reactor year. Now, what does that mean? So, if you have 440 operating reactors worldwide, that's 440 times 10 to the minus 6, and for 10 years, let's multiply that times 10. That means there's 0.44% of core damage for any reactor in the world over the next 10 years. And it does go up. I mean, it is a cumulative number. So for 50 years, that figures out to 2.18%. And that is what is considered unacceptably high, that 10 to the minus 6 number. So 1 in a million per year is considered unacceptably high. Risk margins at power plants are often seen on something on the order of 10 to the minus 7, 10 to the minus 8, or even 10 to the minus 9 consistently. So 10 to the minus 6 is considered unacceptably high. So keep in mind how conservative that is. And the similar number for large early release is 10 times less than that. So 50 years, 10 to the 1 in 10 million for 440 plants, 0.2%. And keep in mind, these are considered very, very high risks. As in, it would not be surprising to see that 10 or 100 times lower when you look at an actual risk model. In other words, core damage per reactor over 10 years, using these upper bound conservative numbers, is about 1 in 100,000. That's to say 0.001%. And a large early release, which is less than Chernobyl, I might add. Chernobyl burned open for days. We're talking on the order of 1 in a million chance for a reactor over 10 years, using upper bound conservative estimates. Now keep in mind, this is an oversimplification. Usually PRA can get pretty complicated when you look at common cause external hazards, such as regional extreme weather or armed conflict. But these numbers do not take into consideration additional modifications that were put in after Fukushima as well, which includes generators that can be dropped in from a helicopter if the entire region is destroyed. So hopefully that puts things in perspective and makes you feel a little bit safer.
Today, we're going to attempt to speculate where the world's next nuclear crisis will happen. We're going to investigate 3 possible examples of...
And you see, this is one thing that you can't really do. It's kind of like when looking at radioactive decay. I can tell you with confidence that a cesium-137, 50% of it's going to be gone within 30 years. I cannot tell you which individual cesium-137 is going to decay, though. I can just tell you that 50% of them are going to be gone within 30 years. So this is against probabilistic assessments, what he's about to say.
Meltdown causes and the locations where they are most likely to occur. We'll then examine what, if anything, can be done to counter these risks and reduce the likelihood of another devastating meltdown that will haunt generations to come.
All right, let's hear it. Corruption in South Korea, okay?
Let's begin our analysis with a story of corruption and mismanagement that was discovered a year after the Fukushima meltdown just across the Tsushima Strait in South Korea. Due to its lack of fossil fuel resources, South Korea began aggressively establishing nuclear power facilities in the 1950s. By the early 2000s, South Korea's 23 reactors fulfilled about 1/3 of the nation's energy needs. However, cracks in South Korea's nuclear power industry started to become evident in 2012. This is when a cooling system failure lasting nearly 12 minutes at South Korea's Kori-1 nuclear reactor plant resulted in a rapid and dangerous temperature spike. Managers at the plant attempted to conceal this event by destroying records, even though they were obligated to report it to the Nuclear Safety and Security Commission. Despite the attempted cover-up,
that's their equivalent of the Nuclear Regulatory Commission within the US.
The event was eventually reported a month later. The resulting investigation found that the incident was caused by a failure of operators to follow multiple safety procedures. South Korea's nuclear power industry would sustain another blow shortly after this event when a dangerous system of bribery, collusion, and corruption, referred to as the nuclear mafia, was identified by a whistleblower.
That's always concerning when any operations crew doesn't follow their procedures. That is one vulnerability that any system that involves the use of people. Safety culture must be cultivated throughout the organizational structure. One of the reasons why constantly reassess, not just by the federal government internally, and through consulting groups like WANO, that's the World Association of Nuclear Operators, which have higher standards than the regulator.
Investigation determined that in the past decade, over 10,000 safety tests have been falsified for components installed in over half of South Korea's nuclear reactors. Companies responsible for these tests either purpose
that so that right there, that wouldn't just get you fired. That would get you indicted. Falsifying safety. I remember learning on early in my career how valuable your signature is when you get a senior reactor operator license. Check, double check, triple check.
Fully skipped examinations or outright fabricated test data to fraudulently approve reactor components. The consequences of this corrupt system became evident in 2013 when communication cables produced by a company called JS Cables caused 2 reactors to unnecessarily shut down. It was later revealed that of the 12 samples sent by JS Cables for certification, only 3 had passed safety tests. Investigations later determined that the 3 passing samples had failed to undergo required radiation exposure prior to testing. These cables had already been installed in 4 reactors and were slated to be installed in multiple other reactors that were under construction. In response to this corruption, nearly 8,000 components installed in South Korea's nuclear reactors had to be replaced. Estimations suggest that this replacement effort cost South Korea's nuclear power plants over $8.4 billion. Analyses of South Korea's
and damage to their infrastructure just by having to shut them down to replace all of that. That's probably the majority of what's included in the $8.4 billion is the downtime. And that's the big thing with nuclear power. One of the biggest advantages of nuclear power is you don't have to turn them off very often to refuel. However, if you need to replace something or something like this happens, the downtime costs can add up quite a bit. And supply chain trust is safety critical. Falsified parts and bad documentation do undermine defense in depth.
Nuclear power industry identified a highly centralized system in which 2 state-owned entities were completely responsible for operating power plants and procuring reactor components. Additionally, investigations identified a personnel pipeline where managers retiring from these state-owned entities would be hired at companies that tested and supplied reactor components. These employees were then susceptible to manipulation and bribery from their former employers. Eventually, 68 of these individuals were convicted and sentenced to serve a cumulative 253 years in prison.
Good, get them. Can't tolerate that kind of stuff.
The fallout of South Korea's corrupt and negligent approach to nuclear energy is also not contained within its own borders. South Korea has expressed a desire to provide nuclear reactor construction and operating services to other countries since the early 2000s. Their first contract was awarded to the United Arab Emirates in 2009 to build and help operate Abu Dhabi's Barakah nuclear power plant. South Korea took aggressive measures to secure this contract.
A lot of people I know within the industry actually went to go over there from the United States. It was a big project.
From the UAE. Engineers removed important safety features from reactor designs to offer a more affordable price. The South Korean government even signed a secret defense agreement with the UAE to sweeten the deal. This agreement obligated the South Korean military to intervene in an Emirati conflict. The Barakah plant was under construction when news of South Korea's nuclear corruption broke. Investigators determined that faulty parts had been used in the construction of the Barakah plant, which delayed its opening by about 3 years. South Korea's government has taken steps toward
that gets expensive fast, delaying a project like that for 3 years.
Building safeguards to protect against corruption since the discovery of its nuclear mafia, but it's difficult to say how much the South Korean nuclear power industry has recovered since the scandals of the 2010s.
And the big loss, so even after they made their reforms, the appropriate people were indicted, their cases heard, they were convicted. The bigger damage is going to be to public trust in nuclear, because this helped fuel some anti-nuclear policies. Even though it's really just, at this point, it has nothing to do with nuclear power in the sense of one form of generation being superior to another. It's a profound systemic failure rooted in corruption, collusion, and weakness within their regulatory body, considering how deeply it penetrated throughout companies, their government, other governments. I would say the bigger lessons learned is about sustaining, cultivating, and safeguarding your own safety culture and having ethics in your leadership positions.
The system is highly centralized and susceptible to the same pressures that affected it previously. It also appears that safety issues are still prevalent. As recently as 2019, operators continued to keep a reactor active for 12 hours after the core began to rapidly overheat. Simultaneously, South Korea is still attempting to secure contracts.
There was no core damage in this case, though.
To build reactors abroad. In 2022.
more lessons learned about safe operator practices, which are reinforced throughout Wano visits and these sort of stories being shared. Like, we obviously don't want to wait for the meltdown to happen before we get the lessons learned.
South Korea was awarded a contract to build 4 nuclear power facilities in Egypt. They are also currently attempting to finalize deals to build plants in Wales, Poland, and the Czech Republic. While we have focused on the case of corruption and negligence in South Korea, it is worth noting that these issues are not completely unique to this country. Indeed, significant corruption has been uncovered in the nuclear power programs of over 15 countries. We only know as much as...
And keep in mind, corruption isn't unique to the nuclear industry. It shows up in just about every industry and every fact of life, which is unfortunate.
We do about the corruption in South Korea because a whistleblower chose to reveal it. Activities that are just as bad or even worse could be taking place right under our noses.
So, obviously, any sort of corruption anywhere, especially within the nuclear industry, is concerning, to say the least. However, it does not mean reactors are on the verge of meltdown. Even with faulty parts, these nuclear plants still have redundant safety systems. Any failed cable or failed valve is not going to automatically cause a meltdown. Even if operators don't follow some of their procedures, that by itself isn't going to cause a meltdown either. Some of these procedures, depending on what the initiating event is, are a matter of verify your automatic safety systems do what they are designed to do. And if they don't, make it happen. And this, while difficult to quantify in terms of corruption, what is quantifiable using probabilistic risk assessment is having systems out of service, such as faulty cables, faulty valves, everything associated with that, and that 1 in 10 to the 6 power reactor years still takes that sort of thing into account.
And we might not know about them until it's too late.
Too late as far as people getting away with corruption, sure. Too late as far as meltdowns, again, 1 in a million chance per year. And that's at the highly conservative end.
In the next chapter of our analysis, we're going to examine the nuclear power facilities in India. Specifically, we're going to focus on India's coastal regions, where nearly 2/3 of their nuclear power facilities are located. It's worth stating that this trend's not uncommon. Countries often build nuclear power plants on coasts, where the massive volume of water required to cool the reactors can be easily sourced from the sea.
Yeah.
However,
They're often use bodies of water, rivers, lakes.
Uncommon is a country like India with multiple coastal plants that are also flanked by active underwater earthquake zones. To India's northwest, the Makran subduction zone in the Arabian Sea has been responsible for earthquakes that caused multiple tsunamis. In 1945, a magnitude 8.1 earthquake produced a tsunami that damaged some of the very regions of northwest India where nuclear power plants are located today. To India's east, the Sumatran subduction zone in the Indian Ocean also possesses a record of producing violent tsunamis. In 2004, this region was the site of the most powerful earthquake that has been seen on Earth since 1964.
That was a horrific tsunami. I remember that.
Quake produced a tsunami that battered India's east coast and even flooded a nuclear power plant there. Fortunately, this facility then automatically shut down, preventing disaster.
And that's why a lot of people don't know about that one. People know about Fukushima, but not this site. Indian coastal nuclear power plants are designed with tsunami hazards in mind, especially after 2004, additional protection was added.
We might assume that this type of sobering experience would be enough to encourage India to reconsider its placement of nuclear facilities, but we'd be wrong in doing so. Since the 2004 tsunami, 1 additional nuclear power plant has opened on India's east coast, with construction planned to begin on another facility in 2025. Although safety features were successful in preventing disaster in 2004, it is useful to compare this event to the 2011 Fukushima tsunami. The Fukushima facility possessed the same safety features as the plants located on the coasts of India. Due to these features, only 1 of Fukushima's 4 reactors experienced a meltdown. But even though the safety features worked in 75% of Fukushima's reactors, we saw how devastating a single reactor meltdown was. Perhaps it would be worth considering just building these facilities on higher ground.
Okay, so after Fukushima, global regulators did require plant modifications afterwards, such as hardened backup power, additional watertight doors, and passive cooling systems. That is to say, the flood, the tsunami can come in and the safety systems will still actuate. The core is still safe. And sitting on higher ground simply isn't always feasible for intake cooling. But you can use other safety systems. You can have breakwaters. You can have elevated backup generators. You can have seawall improvements. You can have remote facilities that can bring in additional backup generators, such as the Flex post-Fukushima response within the United States. And what's unique about that is the event that you prepare for isn't a tsunami, isn't an earthquake, it isn't a hurricane or a typhoon. It is that you will lose all AC power, including your backup diesel generators. That is when you enter those procedures. That is to say, you make an emergency plan call that you're going to enter what's known as an extended loss of AC power event. All that Flex system gets mobilized. Hence the term Flex. It provides you extra flexibility. Why is he putting radiation symbols over the cooling tower? He didn't in any of the other ones.
In our final example, we're going to return to Ukraine, where Chernobyl showed the world just how devastating a nuclear meltdown could be nearly 40 years ago. Today, we're going to discuss the Zaporizhzhia nuclear power plant. This plant is Europe's largest, containing 6 reactors and producing up to 20% of Ukraine's electricity.
You see, that one's big. It has both cooling towers and a large reservoir.
In recent years, it also tends to be surrounded by conflict. The Zaporizhzhia power plant began to capture the world's attention when conflict erupted in eastern Ukraine between pro-Russian separatists and Ukrainian armed forces in 2014. Battles took place as close as 200 kilometers from the plant before drifting further away. This made observers a bit nervous, but this would not compare to the anxiety they'd feel several years later. Russia launched its full-scale invasion of Ukraine in February of 2022, with a particular focus on Ukraine's easternmost regions. The world watched with fear as Russian forces crept towards Zaporizhzhia Oblast and then finally to the power plant. By March, a full-fledged battle was taking place at Europe's largest nuclear power plant. Any damage sustained by the cooling systems or reactors could quickly give rise to the world's next nuclear meltdown.
So here's one thing I will say. Nuclear power plant safety design does not include designing it for a sustained military attack, especially if you're trying to destroy one on purpose. This is definitely a unique hazard scenario. But in this case, the reactors are shut down and cooled. The reactors are cold in cold shutdown. That is to say, not only is the reactor offline, but you've also cooled down and depressurized to reduce the total amount of energy in the system. And the fuel and the spent fuel pools are underwater. Heat generation is a teeny tiny fraction of full power. Passive cooling by itself can keep it safe. Technically, one of the reactors is what's known as hot shutdown, and that's just so it produces just enough steam for waste tank processing, which you definitely need to do. That is a very well-managed and calculated risk that you still want to process your waste tanks. And you have one of the reactors produce just a little bit of energy, all from decay heat, in order to continue that process. But even with that, the International Atomic Energy Agency is pressing for an external boiler, so you can take all 6 into cold shutdown. And that would be safer long-term, because it looks like it's going to need to be in this state for a while.
Russia captured the power plants by mid-March, but this was far from the end of the saga. Russia initially refused to cooperate with the International Atomic Energy Agency's efforts to assess damage at the plant, leaving the world wondering how dire the situation truly was. The agency's investigation finally took place in September, and its findings offered a sobering look at how close Europe had come to a nuclear disaster. The plant had sustained considerable damage during the battles. A high-caliber round had penetrated the outer wall of a reactor, and an artillery shell had struck dangerously close.
No. The outer wall of a reactor containment building, not the outer wall of a reactor. Those are not the same thing. It was superficial damage. No breach of containment, no radiological release has occurred.
To another. A new concern emerged in June of 2023 when the Kakhovka Dam was breached. This dam formed the reservoir that provided water to cool the power plant's reactors. Fortunately, the situation was not as dire as it could have been because 5 of the 6 reactors have been shut down and no longer required intensive cooling.
6 of the reactors have been shut down. Hot shutdown is still shut down. In fact, hot shutdown is still very far away from operating. There are 6 modes of operation. Mode 1 is when you're producing power. Mode 2 is when you're starting up the reactor. Mode 3 is a hot standby. So the reactor pressure vessel and its coolant system have heated up and are ready to start the reactor. The reactor is subcritical, offline, but it is at normal operating pressure and normal operating temperature. Mode 4 is a hot shutdown, which is kind of a transition period. So temperature is above 100 degrees Celsius, but way below normal operating temperature, which is over 350 degrees Celsius. And then mode 5 is cold shutdown, less than 100 degrees Celsius. And mode 6 is you've taken your reactor vessel apart and you're refueling it. So it is not accurate to say that one of the reactors is not shut down.
The International Atomic Energy Agency responded by installing 11 new underground wells to provide enough water to cool the last operational reactor.
Again, not operational. And underground wells would not be enough to cool an operational reactor because of the higher water demand.
The Zaporizhzhia power plant continues to be engaged with the ongoing war in Ukraine. The area is...
I guess you can argue it's operational and that it's supplying steam to your waste holdup tanks, but that does not mean it's making fission or producing electricity. But I've never heard anyone refer to that as operation.
Plagued by active conflict, including a drone attack that damaged multiple reactor containments in April of 2024. Some
superficially damaged them.
Reports also suggest that Russia is storing heavy weapons on the grounds of the facility, although Russia disputes this claim. The American Nuclear Society has said...
Now that is concerning, as that would contravene International Atomic Energy Agency principles and would raise operational safety concerns, even if they just stored equipment that was completely inert. They're taking up space, they're doing things that they're not supposed to be doing, given their reactor's design. It's not going to cause a meltdown or radiological release, but I'm not saying I'm not concerned about that.
In a press release that, given its current dormant state, the Zaporizhzhia power plant is not likely to be responsible for a major radiological disaster. They stated that even if a reactor was breached and radioactive material was exposed, only the immediate vicinity of the plant would be threatened.
Yes, and again, that would be doing it on purpose, as in this would not be an accident. This would be a deliberate act to try to breach a reactor containment vessel through a direct hit with a bunker buster type weapon of some sort.
While the Zaporizhzhia power plant itself may not pose an immediate threat of nuclear meltdown, it is worth thinking about this in a broader context. A war is currently taking place in Europe, where 40% of the world's nuclear reactors are located. An escalation of hostilities could easily threaten other nuclear facilities and give rise to a new crisis.
Sure, I'm not going to debate that the war is a crisis. I mean, at that point, the status of the nuclear power plants is probably the least of your concerns, a rapidly escalating war. But ultimately, the nuclear sites in Ukraine remain stable, monitored, and physically secure thanks to the cold shutdowns and one hot shutdown, redundant cooling and power systems, additional infrastructure such as the wells, and there is IAEA on-site presence.
Humanity is forced to contend with few existential threats more concerning than nuclear radiation, and the event most likely...
Nuclear radiation is not an existential threat. An existential threat would be something like an asteroid 50 kilometers across colliding with the Earth.
To bring people face to face with this deadly force is a meltdown. Here, we've attempted to predict where the next nuclear meltdown is most likely to occur.
Again, it's probabilistic models, but let's see what he has to say.
And now we'll slightly change the question from asking where will the next nuclear meltdown happen to what can be done to prevent another one from occurring.
All the additional safety systems that were installed post Fukushima, and even before that, the ones post 3 Mile Island, really increased the robustness of diverse, independent, and passive safety systems at a nuclear power plant.
Our analysis gives us some very tangible starting points. In the case of corruption and negligence, these problems should be addressed primarily on a policy level. Nations should seek to diversify the entities responsible for overseeing nuclear power operations and component sourcing, avoiding an overly centralized system like the one seen in South Korea. Countries should also implement laws that reflect the gravity of nuclear power mismanagement. These laws should come with harsh punishments for attempting to exploit these systems for personal gain. Following the discovery of
And they are. I mean, that's a big, broader ask about rooting out corruption. I can't say I'm an expert on managing corruption, but I don't normally associate that by itself with reducing the chance of meltdowns. I just think of engineering designs such as additional backup systems, safety training, and operational security. But sure, I'm not going to debate that rooting out corruption is a good idea.
South Korea's nuclear mafia, the government pledged to ban corrupt suppliers from government contracts for 10 years. In reality, the ban only lasted 6 months. If we truly wish to prevent mismanagement of nuclear facilities, these crimes must be taken more seriously. The solution to nuclear meltdowns caused by natural disasters is very straightforward. Don't build nuclear facilities in locations prone to catastrophic events like tsunamis or volcanic eruptions.
There is a whole section of regulations for reactor site criteria that looks at all of this. Extensive site analysis is done early on before you would even get permits from the locals, from the city, the county, or whatever local authority you're dealing with.
Are two of the most destructive natural disasters, and they pose a serious threat to any nuclear power plant in existence. Fortunately,
if you put them in literally the most vulnerable area, sure, but you could say that about any structure.
It's quite easy to predict where these events are going to occur, with tsunamis occurring on coastlines near active earthquake zones and volcanic eruptions occurring near volcanoes. Simply choosing to build nuclear power facilities elsewhere could prevent the world's next nuclear disaster. The most difficult nuclear meltdown threat to navigate is war. While regulations have already been enshrined in international law to prevent attacks on nuclear facilities, controlling aggressors is often difficult in practice. However, even though the situation in Zaporizhzhia made onlookers nervous, the events that unfolded do offer some room for optimism. Despite being caught within a vicious struggle between two nations, these parties eventually cooperated.
This I agree with. And it also shows how little the plant was effective and how effective their shutdown procedures were. That was what they did when they were under attack.
Allow the plant to be inspected. This kind of cooperation and respect for intergovernmental agencies will play a crucial role in avoiding nuclear crisis during future conflicts. History would suggest that since nuclear meltdowns have happened before, they will happen again. But this statement doesn't.
But probability shows that it's not likely. I mean, sure, things will happen. You can use probabilistic risk assessments for Earth getting collided with an asteroid greater than 50 kilometers across. That will happen eventually over the course of millions of years.
Doesn't necessarily have to be true. Indeed, if we learn from history, perhaps we can significantly reduce or even eliminate the likelihood of another meltdown taking place. We've examined 3 locations.
Or the real thing is, the big thing is the large early release. Because meltdown but contained, that's not the scary thing. That's what people think is the scary thing, but that's not the scary thing. As far as eliminating, though, the Chernobyl event specifically, the prompt criticality event, that's been eliminated because you just can't load your fuel that way. You can't defeat your safety systems that way. I mean, if you try to do that, the reactor will shut itself down. It's a hard interlock now. So that I can say confidently that the prompt criticality event has been eliminated.
Would be the site of the next nuclear meltdown for 3 distinct reasons. However, through careful application of policy, diplomacy, foresight, and maybe a little bit of luck, perhaps the answer to the question, where will the next nuclear meltdown happen, could be nowhere.
And again, you need to frame that as in a function of probability, map out the risk, and then mitigate the risk, just like you do for any other engineering solution. Thanks so much for the recommendation, and thanks so much for watching. I'll see you next time.